Welcome back to the Lowdown on Physics. This is a momentous occasion because today we'll be looking at equilibrium conditions. This is the final screencast for Area of Study 3, which is Structures and Materials, and this is the final screencast, or the final bit of the topic for VCE Unit 3 Physics. Okay, so let's look at the term equilibrium. What do we mean by equilibrium? Basically, it's another way of describing something that's balanced. So in the context of this topic, we're looking that all the forces are balanced. So the object will be static or not moving, and we're talking in terms of a net force of 0. So in a simple case, we're talking about the weight force of an object being balanced by the tension in the rope here. But that's simply one dimensional. We can go a little bit more complex. So we'll be looking in two dimensions in this topic, and when we get two dimensions, especially if we haven't got one that's completely vertical or completely horizontal, we're going to need to look at it in terms of components. So given angles, we're applying a bit of trick. So looking at this, we're talking 60 degrees here, and therefore we'll be looking at the vertical component of T2 being T cos 60. We'll look more in depth at going through the analysis shortly, but let's sort of start off with some basic two-dimensional analysis. I know I've mentioned it before, certainly in class, possibly in one of these screencasts, that the concept of the center of mass, where basically it's that single point at which all of the gravity is assumed to work through. Now, every object has a center of mass, and basically we consider the gravitational force of the object the gravitational force to be acting directly through the object at that point. So for just a beam, it would be in the very center if that's a uniform bar. However, if we add some uneven weights, then it's going to be heavier at the right end than it is the left, and so the center of mass is going to appear somewhere shifted to the right slightly. Now, if we're talking a more complex structure, then it's more than just a matter of the net force up balancing the net force down. So if we're in a complex structure, we've got three conditions that we need to meet. Firstly, all the vertical forces must add to 0. Same for horizontal, we're in two dimensions, so we've got vertical forces up, vertical forces down, and all of the torques. Now this is a new concept. It's what we could also call a turning moment. Now basically the forces that would cause it to turn in a clockwise direction would be balanced by any that would make it cause turn in an anti-clockwise direction. So how do we analyze, or how do we calculate torque? Basically it's the turning point about a pivot. So if we pivoted it one way, forces are going to be acting to cause it to turn clockwise, forces are going to cause it to turn anti-clockwise, and so therefore those have to balance. And this is a very powerful analysis tool that allows us to work out the forces acting in different structures. So it's a force that's going to cause a rotation. Now how do we calculate that? We use the symbol tau. Torque equals force times distance. And not surprisingly, it's measured in Newton meters, newtons times meters. Now if the force is going to cause the object to rotate, the force can't be parallel to the object, it must be at right angles to the object to get maximum turning force. So really important to note here is the force and the distance are always perpendicular to each other. If the force, of course, is not at right angles, but it's at some other angle, then you use the component that is perpendicular to. So we'll be able to look at that in one of the later examples. Okay, so let's consider an example, basic example. We've got a 100 kilogram beam. It's balanced at both ends by support A, support B. Let's presume that they're acting from the very end of the beam. So we need to analyse and determine the force that each of these beams, each of the supports would be providing. So basically, what we're going to do is introduce this concept of moments. Now, to look at this, we can kind of sort of say, well, it's 100 kilograms or 1,000 newtons, therefore each has to be providing an equal amount. But what happens when we put other objects on there? So let's analyse it in the easiest scenario, and then we will just sort of make it a bit more complex. So taking moments about A, what that means is, let's make A the pivot point. Have a look at what the forces would then do. If this was a pivot, the centre of mass would cause this to swing in a clockwise direction. However, it can't go because the force from support B acts in an anti-clockwise direction. So the torques are balancing each other out and keeping it stationary. So how do we analyse this? So the sum of all of the torques in the clockwise direction, CW subscript, are balanced by all of the torques in the anti-clockwise direction, AW. Now, force times distance is your torque, so hence the Fx subscripts, CW or AW. So the sum of all of them, in this case, simplest scenario, we've got one torque this way, one torque that way. So force is 100 times 10 to put it into newtons. That's a trick that you need to be wary of for your exam. Make sure it's always in newtons, times the distance, or it's the centre of mass, it's halfway along this beam, assuming it's a uniform beam. We're not given any other information to suggest otherwise. So that's going to be 25,000 newton meters. So we've got the force from support B acting at 5 meters from there, so force times 5. Collecting like terms, 25,000 divided by 5, 500 newtons. Not a big surprise, being that it's 1,000 newtons, it'll be equally shared because it's equidistanced from each of them. So what about support A? For argument's sake, just for getting used to the process, let's do the same thing. Let's make this the pivot. We've now got an anti-clockwise force, and we've now got a clockwise torque. So F of A times 5 must equal 100 times the 10 to put it into newtons, times its distance from the support, which is 2.5. So 25,000, we'll divide that by 5 again. It's just 500 newtons. Now, quick question. The vector sum of the forces are equal to 0. So does 500 up plus 500 up plus 1,000 down equals 0? Yes, it does. So therefore, we'd be feeling pretty confident that we have done this correctly. So let's make it a little bit more difficult, and let's throw a 20 kilogram cat 2 meters from one end onto the beam. Yeah, heavy cat, but you know, let's make it a little bit more exciting by a little bit more weight. Now, what do we need to do? Same process. We're going to take moments about A. So this is our pivot point. So our distances all come from our pivot point. So it'll be 2 times the distance of the cat, 2.5 times the distance of the centre of mass. Both of those are acting in the clockwise against the torque in the anti-clockwise direction. So sum of clockwise versus sum of the anti-clockwise. We have 20 times 10 times 2, so that's the weight times its distance, plus centre of mass times its distance, must equal 5 times F of B, or F of B equals 580 newtons. Once we add those together, divide by 5. Now the total force was 1200 newtons, 100 plus 20, but it's less than half now because the cat is actually offset. So we'll do the same process for moments about B. Sum of clockwise versus anti-clockwise. 5 times the distance from A must equal 2.5 times the 1,000 newtons there, plus 3 times the 200 newtons there, since it's further away. So adding all of that together, divide by 5, we get 620 newtons. Notice here, 580 plus 620 adds to the 1,200 newtons of force that's acting. And just a little check there that does the sum of the forces up add to the sum of the forces down, which we looked at a moment ago. So let's have a look at an alternative way for that second part there. So we found the force at structure B, or support B. The alternate thing that we could have done would be to make sure that the sum of the forces up are equal to the sum of the forces down. So just doing a simple sum there, 1200, or the 1000 plus the 200, must equal support, or force at support A plus the force at support B. So doing the sums, 1200 minus the 580 would give us the 620 newtons. Now what happens if the supports are offset? So this time we will go through exactly the same process. So taking moments about A. Have a think though, firstly, where's it going to be a larger force do you expect? At support A or support B? So moments about A, we've got 1000 newtons times 2.5 must equal the force at support B times the 4 meters, because it's 4 meters from support B. So that gives us 2500 divided by 4, or 625 newtons. So doing the same thing about B this time, we have in the clockwise direction, we have 4 meters times the force at support A is equal to the 1000 newtons times 1.5 meters. So that gives us a force of 375 newtons. Not surprisingly, the closer it is to the center of mass, the greater the force is going to be. And again, double checking, 625 plus 375 is going to add up to the 1000 newtons. So what happens when we introduce forces on an angle? So we've now got horizontal and vertical components. So we would calculate torque in terms of the angle. So for the vertical, say for this example here, we've got a bar, fixed end, taking moments about that. So we've got the force acting on an angle theta. Then we're going to do distance times force sine theta, this component here. So in terms of the triangle, that's our triangle there. Sine theta is the actual force acting down at the point of contact. Alright, let's have a look at a harder example. So this now incorporates a bar that's acting at an angle. So we've got a 5 kilogram basket supported by the structure as shown. There's a beam of 0.4 kilograms that's supported by the strut. The strut's at an angle of 40 degrees. So let's begin by adding this information to our diagram. So we've got 4 newtons down for the 0.4 kilograms. We've got 50 newtons down, that's mass times gravity, 5 kilograms times the G, which is 10. And then you have a force acting from the strut up. There's a force at the wall that's acting down on that angle there. It's going to be holding it that way, and it's also going to be pulling it back to counteract the torque. So let's introduce this here, point X. That way we eliminate this force. Okay, since torque is force times distance, distance is 0, so that torque is 0 if we're making that our pivot point. Then it just becomes an analysis of these two clockwise torques and this anti-clockwise torque. So we've got 0.2 meters times the 4 newtons plus 0.4 meters times the 50 newtons must equal 0.4, that's the distance to this point of contact, times this force, and we need the vector component. We're talking about the vertical direction. Vertical is next to the angle, alternate angles here. So that makes that 40 degrees as well. So we have going up cos 40 degrees. So doing the arithmetic, adding those together, we divide by 0.4 cos 40 to determine what F of S is, which is 67.9 newtons. Now that's greater, F of S is greater than the vertical forces that we've got acting here. But that's because it's providing a horizontal component and the vertical component. So the vertical component would actually add up to 54 newtons. Alright, different example. We've got a child swinging on a rope. We're given all the details there about this child. So firstly, calculate the tension in the rope. So obviously we've got the account for the mass of the rope and the mass of the child who is swinging on this rope. So tension in the rope would just be the sum of the two forces, 400 newtons and 25 newtons, or 425 newtons. Okay, so drawing force diagrams for the horizontal beam. Let's call this support A and support B. So we've got F of A acting here, F of B acting on here. What we're going to be interested in is the perpendicular component. So this is going to be F sine 60 because it is an opposite when we look at that triangle there, opposite over the hypotenuse. So that will be F sine 60 acting vertically. Then we've also got the weight of the buoy and the rope and the weight of the actual beam acting through the center of mass. So calculating the horizontal forces, calculating the forces on the horizontal beam. So we have same process as before. Take moments about A. This eliminates one of our unknown forces, so we're only working with one unknown value, one equation, one unknown. Otherwise we can't work it out. So we have 1 meter times the weight of the buoy and the rope, and 1.5 meters times the weight of the beam must equal 3 meters times the vertical component of that force, which is 3 times F sine 60. So rearranging 725, if I did my maths right, then divide by 3, divide by sine 60, we get a force of 279 newtons in F of B. Now we expect this one to be smaller than that one because the combined weights are closer to F of A than F of B. Okay, same process, moments about B. This takes B out of the equation, makes that the pivot point. We get 2 times the distance to the 2 meters to the distance as the distance. Multiply that by weight of the buoy and the rope. 1.5 again to the center of mass of the beam, and that's equal to 3 times the vertical component of this force. So rearranging, we get F of A equals 442.64 newtons. Now, quick question, why does F of A and F of B, if we do the sums, okay, quick sum, that's going to be greater than 700 newtons, and yet the three forces we've got, 400 plus 200 is 600, 625 newtons acting down. Some of these forces are more. Why is that? So really the reason we've got that is because we're not doing the vector components, the vertical components only. The vertical components of these two forces would add to the 625. However, these two forces have horizontal components as well, and so therefore will add and be greater than the sum of the vertical components. Alright, let's have a look at a question from the 2007 exam. This is a pretty nasty question. You only get multiple choice questions in this section now, but it highlights some really key points to this whole topic, so it's a very good question. So we've got a 20 kilogram street light, we have a cable AB, we have rod BC. assume that their rod and the wire are negligible, because in the ideal world nothing has any mass anyway. So we hinged at point C, makes an angle of 30 degrees. The diagram's not the best because it doesn't give you much of a feel for that actually being 60 degrees, but anyway, we'll work with it. So we need to calculate the magnitude of the force in AB. So before we go too far, let's have a look at the forces. So we've got tension in the cable here, we've got weight of the actual light, so that's what we're after, that's what we know. We can ignore the weight of the cable and the weight of this rod. How nice. And then we're not actually given a length, so we're just going to call that length L. Now, works really nicely in that the only two forces are acting at the same point. So we're going to take moments about C. That means we're then looking at forces that are perpendicular to the rod BC. So here we have, there's our 30 degrees by alternate angles. So we have 200, and that will be sine 30, acting in that direction. And then, since that's 60 degrees in there, that makes that 30 degrees there as well. So that's going to become T, and that's in our triangle here. Okay, that's always the hypotenuse, the actual force. So that's adjacent. So that's going to be T cos 30. So anti-clockwise versus clockwise, we have the length, which is just length L, times 200 sine 30, and that has to equal length L times T cos 30. Now, conveniently, both acting through the same point, therefore, when we do a bit of a division, the L's are going to cancel out. L 200 sine 30 divided by L cos 30, they cancel down. We find that the tension is 115 newtons. So that's a pretty tough question for this topic, but it does highlight some of the ways that we can use moments to calculate that. Alright, the only other thing that we need to look at or consider is what we call a truss system. This is what we'll look at with West Point Bridge Designer, is analysing in beams or in structures which ones would be under compression, which ones would be under tension. Okay, here it's sort of highlighted these ones are going to be under tension and compression based on their colour, looking at which forces are going to be pushing down on them, which ones are going to be stretched. So really, what we need to remember, two important things. Look at each joint separately, and then the sum of the forces at each joint must be 0. So let's analyse a simplified version of the truss system. The easiest point is always to start outside, especially where you know definitely how the forces are acting. So at this support here, it's going to be under compression. Everything's going to be pushing it down, so it's going to have a reaction force pushing it up. If that has a vertical component up, this one must have a vertical component down. So it must also be in compression. So the vertical component here must be equal and opposite to that compression there. Looking at vector components, this one's got a horizontal component to the left. Therefore, the one down here at this point must have a component to the right. That one has a reaction force that's pointing in, therefore it will be in tension as opposed to this in compression. Okay, so we've worked out the first joint. Let's look at the second joint. So this was in compression, that means that it's still in compression at the other end. Now, if that one has a vertical component up, the easiest one to look at then is this one here, which will have a vertical component down, which will be equal and opposite. Okay, and then summing the forces, this one will also be in compression, or if we think about it, as everything sags down, these are going to be pushed together, and so that's going to actually compress that bar. Okay, so we know this one's in tension also, so bring that down. This one was in tension also. So when we look at that, if we've got forces to the left, then we must have forces to the right. Although it appears as if we have all vertical components going up here, we need to consider the weight force that's acting down at that point also. So that will balance out the upward forces. Okay, and so then you could systematically, analysing or using the fact that this is in tension, that's in compression, work through and systematically work out each of the different bars to work out whether it's in compression or tension. Alright, that's it. That is the last piece of information for Unit 3 VCE Physics. Happy studying. See you in class.